Here we have a 460 volt, 60 hertz, 4-pole, 1740 RPM, 3-phase induction motor, whose equivalent circuit per phase parameters are as follows. R1, 0.25 ohms, X1, 0.5 ohms, R'2, 0.2 ohms, X'2, 0.5 ohms, and XM, 30 ohms. Our task will be to calculate the starting torque when the motor is started at full voltage. At standstill, the slip is equal to 1. This means that all of the air gap power is dissipated as rotor copper loss. No mechanical output exists, but the air gap power still produces torque. The starting torque is found from the rotor power equation. We use the starting torque, tau, to equal 3 times the magnitude of the rotor current squared multiplied by the rotor resistance and divided by the synchronous angular velocity omega s, where I'2 is the rotor current referred to the stator. R'2 is equal to the rotor resistance referred to the stator, and omega s is equal to the synchronous speed in radians per second. The first step in calculating the magnitude of I'2 is to calculate the per phase voltage V1. V1 is equal to the phase-to-phase voltage 460 divided by the square root of 3, which is equal to 265.581 volts. From the per phase values, we know that the stator impedance is equal to R1 plus JX1. Plugging in our actual values, we get 0.25 plus J 0.50 ohms. We also know that the stator impedance is equal to R'2 plus JX'2. Plugging in the actual values here, we get 0.20 plus J 0.50 ohms. And finally, we know that the mutual impedance is equal to JXM, and the actual value of that is J 30 ohms. Combining the rotor and magnetizing parallel provides us with this equation. 1 over Z parallel is equal to 1 over ZR plus 1 over ZM. 1 over ZR in real terms is equal to 0.2 minus J 0.5 all over 2 squared plus 0.5 squared, which reduces to 0.689655 minus J 1.724138. 1 over Zm, which is equal to 1 over J 30, which is equal to a minus J 0.3333. Therefore, putting real numbers in for 1 over Z parallel, we get ultimately 0.6896 minus J 1.7574. Inverting 1 over Z parallel, we get Z parallel equal to 0.19353 plus J 0.49325 ohms. The total input impedance per phase, Z1, is equal to ZS plus Z parallel, which equals 0.25 plus J 0.50 plus 0.19353 plus J 0.49325. That reduces to 0.443 plus J 0.993 ohms. The voltage across the parallel branch, using the voltage divider rule, V parallel is equal to V1 times Z parallel divided by Z1, which equals 265.581 times the quantity 0.486 plus J 0.023, and that equals 129.0 plus J 5.98 volts, the magnitude of which is 129.34 volts. We are now in a position to calculate the rotor current referred to the stator. I'2 is equal to V parallel all over the rotor impedance, which is ZR. And that is equal to 129.20 plus J 5.98 divided by the quantity 0.20 plus J 0.50. And that equals 99.419 minus J 218.633. And I'2 magnitude equals 240.17 amps. We now can calculate the starting torque. The synchronous speed in radians per second for a 4-pole 60 Hz motor is equal to 120 F, the frequency, divided by P, the number of poles, or 120 times 60 divided by 4. And that is equal to 1800 RPM. We now need to convert that to radians per second, which is omega S, which may be found by equating it to 2 times the revolutions per minute times pi divided by 60, and that equals 2 times pi times 1,800 divided by 60. That equals 188.496 radians per second. The starting torque will now be calculated using the following terms to give us 185.2 Newton meters. Ready to go beyond just solving problems? If you've been following my daily post and enjoying the sample problems, you're going to love this. All of these problem sets and more are now available, or soon will be, on my official course site, my standstore for electrical training. Just go to the web address that you see at the bottom of this slide, https://stand.store/GVB. In recent years, the reality of climate change has become impossible to ignore. Severe weather events are growing more frequent and more intense. For homeowners, this means that utility power outages are no longer inconveniences. They can last for hours, days, or in extreme cases, even longer. The question is no longer if, but when. You'll need a solution to keep your homes powered and your family safe. Now is the time to prepare and ensure that you're not left in the dark when the next storm hits. Here are some trusted resources to help you prevent power outages at home. 𝐃𝐈𝐒𝐂𝐋𝐀 Canada at this web address, 𝐃𝐈𝐒 USA at this web address, Bluetti Canada at this web address, Bluetti USA at this web address, and Bluetti Australia at this web address. And finally, you can get EcoFlow at this web address.